Hello and welcome back to another lecture. Today I'm going to cover section 10.4, which is talking about adding, subtracting, and multiplying radical expressions. This is really an extension of 10.3, going a little bit further along. Okay, so that being said, I want to discuss first if I have something like 2x plus 5x. This is not necessarily on your actual lecture notes, but I'm trying to make a point out of this. If I have 2x and 5x, could I combine these terms? And the answer is yes. How do I know? They're like terms. They both have an x variable, and both of those x variables are identical. So they're both to the first power. And so I could combine this, and I get 7x. Now, what did I actually combine here? I combined the 2 and the 5. And so you can think of this as 2 plus 5x, and that is how I got my 7x. Now, what if I had something like 4x plus 3y? Are these like terms? And the answer is no. I have an x here and I have a y. These are not identical variables, and so I cannot combine these terms. Radicals work the same exact way. So check this out. If I had 3 square root of 24 plus the square root of 54, are these like radicals? The answer is no, not currently. I have the square root of 24, I have a square root of 54. These are not identical. This is kind of like this situation here, where I didn't have identical variables. The difference with radicals, however, is that I can simplify these expressions. So let's take a moment and do that. So it's 24, if I were to look at the square root of 24, is 4 times 6. I can pull this 4 out, and so I'm left with the square root of 6 here. Now notice I carried my 3 coefficient all the way down. This is a multiplication process in between, so once I pulled that 4 out as a 2, I am multiplying. So I'm going to simplify these vertically as I go through the process. 3 times 2 is 6, and I have square root of 6 there. I am adding, so I'm going to just bring my sign all the way down. I know I'm adding in my expression once I get down here. Let's talk about 54. 54 can break down into 9 times 6. Square root of 9 can be pulled out. The coefficient value out here is implied as 1, so that's like a 1 times 1 times 3 once I pulled that value out. So that's really just 3, and I'm left with square root 6. Now let's reevaluate our position. Are these like radicals? The answer is yes. These are identical radical values. They are both square roots of 6. Same index, same radicand. Very good. That means I can technically add my coefficient values of 6 and 3. So it's kind of like saying 6 plus 3, square root of 6. So I get 9 square root of 6 as my end result. And that's the entire process if you're adding or even subtracting your radical expressions. Let's try another one. I'm going to put a little dividing line there. So I have 2 square root of 20x minus the square root of 45x. Now, if I'm looking at these terms, are they currently like radicals? The answer is no. But can they be? Let's see. Let's see if we can simplify them. So 20 can be simplified, correct? So I have 2 from here. Square root, 20 can be 4 times 5. And I still have this x, so 4 times 5 times x, if you will. This 4 can be pulled out as 2, so I have 2 times this 2 that I just pulled out. Square root, I have left over 5x. This is 4 square root of 5x. I am subtracting, so I'm going to bring that down. Now let's talk about that 45. Square root of 45x can be broken down, so I have 9 times 5 times x. I can pull out a 3 here. There is only a coefficient of 1, so I'm just going to pull that 3 out. And I'm left with 5x left over. Now, are these like radicals? The answer is yes. They have the same root index and the same radicand values. So I can combine these. That's like 4 minus 3, which is 1, and I have square root of 5x left over. You can also rewrite this, because of this being a 1 coefficient, as just the square root of 5x. Either solution is correct there. Let's try another one. Let's say I have 2 square root of 11 minus the square root of 11 plus 3 square root of 44. Just so I don't run into this other problem, I am going to erase it for my board space. 11, can it break down? No, it's a prime number, leave it alone. So you have 2 square root of 11 minus square root of 11, we'll come back to that. 44, square root of 44, can I break that down? Yes. 44 breaks down into 4 times 11. There is a perfect square that I can pull out here. So I have 3 times 2, the 2 coming from here, square root of 11 left over. That is 6 square root of 11 here. I was adding that term, so I still am. And I have that minus square root of 11 and this 2 square root of 11. So I just brought these two terms down, even though I did nothing with them. They were already simplified as much as they could be individually. At this point, do I have like terms or like radicals? Yes. So I'm going to combine what I can. So I essentially have 2 minus 1 plus 6 square root of 11. 2 minus 1 is 1, plus 6 makes this 7 square root of 11. So very simple, very easy process. You just have to take it step by step. Solving these vertically is also a very good tip. That way you can see the process as you're going all the way down. All right, this next example, I have 5 square root of 12y cubed plus 6 square root of 75y cubed. Are these presently like radicals? The answer is no. Can I simplify them? Let's see. 12 can break down into 4 times 3. The y cubed can break down as y squared times y. I can pull out a perfect square here and here. So I have 5 times 2y, square root, I have 3y left over. This comes out to 10y, square root 3y. I am adding. Over here, I have 6 times, my 75 can break down as 25 times 3. Y to the third can break down as y squared times y. I have a perfect square here and here. So I have 6 times 5y, square root 3y left over. This comes out to 30y, square root of 3y. Now there is a very important point that I'd like to make at this stage. Because we have y's both in and out of the radical, we need to make sure that our terms are like terms and that we have like radicals. So I do have like terms, because this is 10y and this is 30y, so identical y variables here. And I have like radicals where this is a square root of 3y and a square root of 3y. So I can combine these. That's like 10y plus 30y, square root of 3y, or 40y, square root of 3y. So very important point. Again, working vertically, you can see every step. try this next problem. Then we'll move into the next stage. So I have 2 square root of a fraction 75/16 plus 4 square root of another fraction, but it is going to be the square root of 8 over the square root of 32. Currently, they are not like radicals. Now, I do want to make sure that I take my time here because I'm seeing some different components, different radicals all around. So I'm going to work on the first one first, going vertically like I have been. Square root of 75 can break down into 25 times 3. Square root of 16 is 4. So I have 2. I can pull out a 25 here. So that's going to be 2, 5 radical 3 over 4. This 2 and 4 can simplify because this is like 2 over 1 technically. So 2 and 4 can simplify. That leaves you a 2 in the denominator. So that is 5 radical 3 over 2. I am adding. Let's look at this next part. I'm left with 4. I have the square root of 8, which is 4 times 2. I have the square root of 32, which is 16 times 2. Perfect square of 2 here, perfect square of 4 here. So that's 4 times I have 2 radical 2 over 4 radical 2. Now, the 4 and the 4 can cancel. The radical 2 and the radical 2 can cancel. So that leaves me just 2. And this would be just fine. However, because we're looking at simplifying everything here, we're looking at, do we have common denominators? The answer is no currently. So I'm going to go ahead and combine this into a single fraction. I have to multiply this by 2 over 2. And so that will be 5 radical 3 over 2 plus 4 over 2. Combining this, I would have 5 radical 3 plus 4 over 2. So this would be the fully simplified version of that particular problem. So that is the fully simplified version. Okay, now that is it for adding and subtracting. Let's get into multiplying. Multiplying radicals is similar to what you've done in the past with a slight modification. You'll see what I mean in just a moment. Let's say I have a problem where it's 7 minus the square root of 3, and I'm multiplying against the square root of 5 plus the square root of 2. So I have binomial multiplication here. I could technically FOIL. That's perfectly fine. You can still do that. So first terms, I have 7 square root of 5. Outer terms, I have 7 square root of 2. Inner terms, I get negative square root of 15. Because remember, 3 times 5, they have the same radical index. And then I have these square root of 3 times square root of 2, negative square root of 6. At this point, I would look to see if there's any like radicals or if anything could break down to give me like radicals. And in this particular answer, that is no. This is as simple as it gets. Now, check this out. This part's really cool. And you'll see something very similar to what you've seen in the past. So I want to just get it written down first, see if you see it. I have square root of 10 plus square root of 3 times the binomial of square root of 10 minus square root of 3. These are identical terms with opposite operation. These are conjugates. And you know something about conjugates that are being multiplied. Conjugates, such as this in binomials, creates a difference of squares. So essentially you're looking at radicals with the difference of squares. That's pretty cool. Let's see how it works. Let's see what happens here. First terms, that's square root of 100. That's square root of 30 for the outer terms. Inner terms, that's positive square root of 30. Last terms, that's minus square root of 9. These two are like radicals already. I have a -1 and a +1. Those cancel out. Square root of 100 is 10. Square root of 9 is 3, so that's 10 minus 3, which is 7. Huh. So notice, through this particular setup, when you're multiplying by conjugates, you have the same exact terms, opposite operation. When you're multiplying by conjugates, you actually can eliminate your radical values. And by doing so, you're left with typically integer or whole value numbers. All right. Let's try a couple more. Let's say I have the square root of 7 minus 3 as a binomial squared. So remember, binomial squared is a little bit different than difference of squares, which we just did. So binomial square, we're actually saying that this is occurring twice. Just like so. We're then going to go ahead and do our FOIL again. So that's going to be square root of 49 minus 3 square root of 7 minus 3 square root of 7, and then plus 9. Square root of 49 is 7. These are like radicals, so I could combine those. That's a -6 square root of 7 plus 9. 7 plus 9 can be simplified, so that is 7 plus 9 is 16 minus 6 square root of 7. And there you are. All right, let's take a look at one more. So I have the square root of k plus the square root of x. And I'm multiplying this against its conjugate. So I'm multiplying conjugates here. And here's what's really cool. I can already jump to the end. But let's say I don't. Let's say I go through this process. Multiply that out. That's the square root of k squared. That is minus kx. That is plus kx. And that is minus the square root of x squared. These two middle terms cancel. That's inherent with multiplying conjugates. Here, I'm left with k. That is a k if I ever did see one. I don't know why I can't write a k today. There's a k, all right, and then minus x. So I'm left with k minus x. And the beautiful thing about conjugates, and you can see that in this case or in this case, is that you are eliminating those radical signs. So it's really cool that way. Okay, so guys, that is it for section 10.4, but stay tuned. I'm going to cover section 10.5, which is rationalizing denominators with square roots, in just a moment.